In this lecture, we're going to be looking at a general method to solve waveguiding problems, which centers on the use of separation of variables to solve the Helmholtz equation. This is a long lecture. It goes through all the steps in great detail on how to do the separation of variables expansion. And as I go through the presentation, you're going to see the parts of the material that I expect you to know, the parts that I expect you to recognize, and we'll talk about how much of the derivation you should be able to reproduce. The learning objectives for this presentation are, first of all, that the students be able to understand how separation of variables work and when it can be used. So you want to know what the general method is, how we go about doing it. And you should comprehend how the separation of variables method produces modal solutions on the types of waveguides we're going to be looking at. Students are not expected to be able to do this derivation from scratch on an assessment. Now, if those of you who are electrical engineers who are going to go on and spend a lot of time working on RF or antenna problems, you will become more familiar with these methods to the point where you could apply them if you had to. If you saw a waveguiding structure and you needed to do a quick analysis, you'd be able to. But in general, there's going to be no expectation that you know how to do this whole derivation. However, it's important that you understand what the steps are and how what spits out at the end, which is the modal solution, is related to the original set of equations, which are Maxwell's equations. In lecture 9a, we demonstrated that so long as we could solve for either h sub z or e sub z, that we're able to determine the other four field components by using the waveguide field equations. And this is very important to us because it allows us to take the vector Helmholtz equation and reduce it to a scalar equation. And as I indicated in the previous lecture, we're going to further split these problems into two categories. We have our TE modes. These are modes where E sub z is equal to 0. And we have our TM modes where H sub z is equal to 0. So we only need to solve the equation for one field component, and then we can get the rest of the mode structure from that one field component. The geometry that we're going to be looking at is a rectangular waveguide. We're going to assume that the waveguide has a rectangular cross-section, that it's uniform in Z, that it's filled with a material that has permeability mu and permittivity epsilon. We're going to assume that these are linear, isotropic, homogeneous, and lossless. The methods that we're developing can deal with more complicated media, but for the purposes of this conversation, we'll assume that they are simple media. We're also going to assume that the conductors that make up the walls of the waveguide are perfect electrical conductors. Right? So that means that inside the waveguide, we can deal with the time harmonic source-free Helmholtz equation. And the only place where we have currents or charges is on the perfectly electrically conducting walls, and there's no loss anywhere in the problem. Now the symmetries of this problem, namely that I've got perfect longitudinal symmetry, right? So this problem looks exactly the same as I move down my waveguide, allows us to write the fields as having a transverse component plus a propagating component. And the transverse component, E sub z or H sub z, which we're going to write as a function only of x and y, we'll deal with the z dependence in a second, I can write them as a product of two functions. I can separate the variables, and I can say that this function of x and y can actually be written as the product of one function that depends solely on x and a second function that depends solely on y. Now I'm going to work progressively through the solution for the transverse electric modes. And I'm not going to do the TM modes because the methods are identical. We'll give you the result for the TM modes. But we're going to work through in great detail the transverse electric modes. And remember, I don't expect you to be able to produce this derivation from scratch. I would expect that looking at your textbook, either of your textbooks, they both develop this, or listening to the lecture, that you can become familiar with these steps. The differential equations and the algebra involved are things that you should have complete command of, right? But I'm not going to expect you to derive this from scratch. So now with the TE modes, and we're assuming, or not assuming, we define a TE mode so that E sub z is equal to 0, right? We are going to write the z component of the magnetic field as the product of our transverse function that depends only on x and y times e to the minus j beta sub z times z. And the notation I'm using here is a little bit different than your textbook. I'm going to consistently use this beta sub z to indicate that this is the propagation in the z direction. Right? And since we've already said h sub z could be separated, I can now write it like this. And notice I've dropped the subscript x sub h and y sub h, and we'll just leave it as x and y. So my function h sub z, which is in principle varies as a function of x, y, and z, I'm actually able to separate it out into three separate components. We're going to define beta sub u as the wave number for a plane wave propagating in an unbound medium that's the same as what's filling our waveguide. So beta sub u is omega square root mu epsilon. And when we take that piece of information and we substitute it into the Helmholtz equation, or we use it to define the Helmholtz equation, we have this behavior here. And our vector Helmholtz equation has now become a scalar Helmholtz equation, where I take three partial derivatives, or second order partial derivatives. So I've got the second derivative with respect to x, second derivative with respect to y, second derivative with respect to z, plus beta u squared times h sub z equals 0. So that's the equation that we need to solve. I can now substitute in my assumed form for h, and we'll see what the differentiation produces. Right, so I replace h sub z with my product of three separate functions, and then I pull things in. The partial derivative with respect to x, that only operates on the function capital X, and it's no longer a partial derivative, it now becomes a complete derivative, as we see here. The partial derivative with respect to y only operates on y. The partial derivative with respect to z, well, I take two derivatives of that function, and that's going to give me minus j beta sub z squared. Right? And minus j times beta sub z quantity squared is minus beta z squared. So my Helmholtz equation in this line changes to this form. And notice I factored out my e to the minus j beta z times z. So now consolidating terms, since I factored out the e to the minus j beta z, and the right-hand side is equal to 0, I can multiply both sides by e to the plus j beta sub z, and it goes away, as we see here. And we have this form for our equation. If I then divide both sides of the equation by x times y, right? On the right-hand side, it was 0, so that doesn't change anything. But on the left-hand side, of course, we're going to see that this y will cancel with this y. This x will cancel with this x. And this x and y will go away completely. And we get down to this expression here. Now, you're going to look at this, and you're going to say, okay, why did you do that? How is that any better? And what I'll say to you is, well, let's take a look at these terms, term by term. This term here is a constant. It does not depend upon x or y. This term here only depends on y. And this term here only depends on x. This shouldn't say z, this should be a constant. Okay? If these three terms are going to add up to be 0, the only way that can happen is if this first term is a constant and this second term is a constant. So what we've done is we've managed to separate our variables so that all of our x action is here, all of our y action is here, and this has neither x nor y action. So when I put these together, what I really got is a case where my x functionals have to add up to a constant, my y function has to add to a constant, and I must satisfy this equation of separation, which says that the sum of these three constants must be equal to the beta sub u. Right? So we said this bit here was equal to beta x squared, this bit here was equal to beta y squared, and this bit here then gives us our separation condition. Now these are equations that we're very familiar with. and we can write the solution as a cosine plus b sine for the function x, c cosine plus d sine for the function y. They have beta sub x and beta sub y, and we're going to solve for these coefficients and these betas in the upcoming slides. Right? And we can consolidate all of this and write our total field, or at least the transverse component of our total fields, is with this expression. The next step in the process for us is to use the boundary conditions at our disposal to find values for the coefficients a, b, c, and d, as well as beta sub x and beta sub y that are going to allow us to satisfy the boundary conditions. Because remember, with the differential equation, it's not just the statement of the equation, it's the equation plus the boundary conditions that specify the entire problem. So the boundaries of our waveguide are indicated here in red, and we're going to evaluate them in some arbitrary xy plane because these boundary conditions need to be met at all z positions. And the boundary condition that we're going to use is the boundary condition on the normal component of the magnetic field. Because remember, at the surface of a perfect electrical conductor, we can either enforce that the tangential electric field is equal to 0, or that the normal magnetic field is equal to 0. And we'd get the same answer either way, but I'm choosing here to use the normal component of the magnetic field. And so at x equals 0, which is this interface on the left, at x equals 0, and at x equals a, then the x component of the magnetic field must be 0, and at y equals 0, and y equals a, the y component of the magnetic field must be equal to 0. And this is the boundary condition that we're going to use. So let's see how that ends up coming into play. And then remember, once we've solved so in order to be able to apply this boundary condition, we need to use these expressions. Specifically, we need to be able to use this expression and this expression to be able to get h sub x and h sub y from the magnetic field. So just applying these equations to our assumed solution for the z component of the magnetic field gives us these expressions here. We have, to get the y component of the magnetic field, we take the derivative of h sub z with respect to y. And so that means that what was cosine sine becomes minus sine and cosine. And to get h sub x, we take the derivative with respect to x. So what was cosine and sine becomes minus sine and cosine. All right, so these are our expressions. Let's start off by looking at the y component of the magnetic field intensity, and we're going to look at the y component of the magnetic field intensity for the position y equals 0. So we're looking at this interface. We're looking at this boundary. Okay? At that boundary, this field component must be equal to 0. So when we substitute in y equals 0, over here in the second half of the expression, we get sine of 0 and cosine of 0. Sine of 0, of course, is equal to 0. No problem. But cosine of 0 is equal to 1. Right? So this cosine here is equal to 1. This is equal to 0. Right? So over here on the right, I'm going to have d. But I need this entire expression to be equal to 0. And the only way that this equation, the left-hand side of this equation, can be equal to 0 for all positions x is if d itself is equal to 0. So we've now just solved for one of our boundary conditions, right? We had two coefficients, we had c and d, and we've now eliminated d from the problem. Next, we can go in and we can take a look at the fields at y equals a. And once again, h sub y must be equal to 0. And at y equals b, this expression becomes as follows. We still have the x components here, which are unchanged. You'll notice that what I've circled here in red is exactly the same as the line above it. But now we have sine of beta y times b. Once again, the only way for this expression to be equal to 0 everywhere is if sine is equal to 0. And that will happen anytime that beta y times b is an integer multiple of pi. Now, any integer multiple of pi will work. It can be pi over b, it It can be 2 pi over b, it can be 3 pi over b, it can be 1,000 pi over b. And we're going to see that each of these solutions corresponds to an allowed mode of the problem. So we have more than one solution to the Helmholtz equation, each of which is going to have slightly different characteristics. So we've solved for d, and we've solved for beta y. That has simplified our problem a little bit, and we can now substitute this in for beta y, and we get this expression here. We've got c, and we pull it out front, and you'll notice that I've said c sub n, because this coefficient, this amplitude for this mode, corresponds to a specific value of n that we see here up in sine. So if I choose n equals 1, I'll have c1 sine of pi y over b. But I could also have chosen n equals 2, so I'd have c2 sine of 2 pi y over b. Those both satisfy the Helmholtz equation, those both satisfy the boundary conditions, and they can both be present on your waveguide. Okay, so now that we've eliminated d, and we've solved for beta sub y, we can consider our second two boundary conditions, the boundary conditions on the x component of the field. Right? So here is our expression, bringing it back from the previous solution. Right? And to get h sub x, we need to take the x derivative. So what was cosine and sine becomes now minus sine and cosine. And we evaluate this at x equals 0. And when I evaluate this at x equals 0, I get a sine of 0. And once again, we have exactly the same situation. This term is 0, so it doesn't cause me an issue. But cosine of 0 is equal to 1. The only way for this entire expression to be equal to 0 for all values of y is if b is equal to 0. So now I've eliminated the b coefficient, just like I eliminated the d coefficient. I now apply my boundary condition at x equals a. So we're over here on this right-hand side, and we have exactly the same situation. Right? And I've got this expression. But the only way that this expression can be equal to 0 is if this sine term is equal to 0. And that happens whenever beta x times a is an integer multiple of pi. Same exact argument. So that tells me that beta x equals m pi over a. And so we had an a coefficient. We have a big A, which is our coefficient, and a little a, which is the size of our waveguide. We can now factor that out front, and I have an a sub m, remember, because this corresponds with our choice of m for beta x, and I have a c sub n, which corresponds with our choice of n, and I'm going to actually combine these two coefficients into a single coefficient, and we'll call that a m n. And so when I choose m and I choose n, that is a mode of the solution. And in the next lecture, we're going to specifically look at the structure of these modes in rectangular waveguide. And in the following lecture, we're going to look at the modes for circular waveguide. And so if it's a little bit uncomfortable, don't worry. You'll see an example of that in a moment, or you can look at your textbook. Either of your two textbooks have the pictures. Right? This coefficient will be the amplitude of that particular mode. And the z component of the field has this form. It's got a coefficient times cosine of m pi x over a, right? So I'm going to have a sinusoidal variation in x. Cosine of n pi y over b, I'm going to have a sinusoidal variation in y. And my choice of n is going to tell how many oscillations that I have inside the waveguide. And the z propagation is e to the minus j beta z times z. So of course, since I've solved for h sub z, I can use the equations. I can just simply plug this value into these equations, take these derivatives, and I get these field values. And these look ugly, and it's some kind of semi-nasty algebra, but it's no big deal. It's stuff that you know how to do. And these are the distributions of the fields that I get. And now these 5 field quantities completely describe the electromagnetic mode. And we would call this the TEMN mode of the rectangular waveguide. And as I said, in lecture 9C, we'll specifically look at the structure of the first several of these modes. Now, we solved for beta x and beta y, and you'll hopefully recall that when we were looking at the Helmholtz equation, we had this condition. We had the condition beta x squared plus beta y squared plus beta z squared was equal to omega squared mu epsilon. I've now just flipped this around. Since we know what beta x and beta y have to be, we can now solve for the propagation constant. And the propagation constant takes this form. Right? It's equal to the wave number for plane wave propagation in an unbounded medium minus m pi over a squared minus n pi over b squared. So you see something very interesting. Beta z is going to be different for the various modes. As n increases, n goes up and up and up and up and up, right? Beta z is going to go down and down and down and down and down. Just as we saw, though, back in lecture 8, eventually we're going to get to the point where n gets so large that n pi over b squared is actually greater than omega squared mu epsilon for a particular frequency. It's actually not n pi over b squared, it's the sum of n pi over b squared and n pi over a squared. Well, let's set m equal to 0. I can keep increasing n until the value of this function under the radical becomes negative. When that happens, beta z becomes imaginary, and that mode is evanescent, and that mode is cut off. Right? So we talked about cutoff frequencies in the context of the parallel plate waveguide. We've got exactly the same phenomenon associated with each of these TE, MN modes. Right? So every mode is going to have its own cutoff frequency. Below that frequency, that mode doesn't propagate on the waveguide. And so when you're actually working with waveguide in a laboratory scenario, you'll get a waveguide that's designed so that its lowest order modes are propagating at a particular frequency. If you go too high in frequency, you'll now have multiple modes that will propagate on that line, and that waveguide will not be designed to work at that frequency. We'll look at the specifics of particular modes for rectangular waveguide in lecture 9C. Now, I'm not going to go through the steps for the transverse magnetic modes. In fact, your tutorial problem is to work through the steps for the transverse magnetic mode. And again, as I indicated, the expectation isn't that you can produce this derivation out of your head. But with guidance, you should understand the derivation, and you should be able to step through the process as you go. As you just saw, it's a little bit tedious and there's some algebra, but it's nothing too hard. And after you go through those processes, the TM modes will give a z component of the electric field given by this expression. Now you'll notice that whereas in the TE modes, the magnetic field z component varied by cosine and cosine, in the TM modes, the z component of the electric field varies like sine and sine. So they're fundamentally different in their nature. As with the TE modes, we'll have a single coefficient that will correspond to the mnth mode. And so we would call each of these modes the TM, MN mode of the waveguide. So we've got a series of waveguide modes that are transverse electric, and another series of waveguide modes that are transverse magnetic. Once again, we can compute the transverse fields by plugging this value of E sub z into our formulas, and we get these expressions here. Again, we have cosinusoidal and sinusoidal variation, e to the minus j beta sub z, z propagation, and our propagation constant, just like we saw in the TE modes, is given by the square root of this difference. Right? And this is exactly the same propagation constant as we had. So the TE mnth mode and the TM mnth mode will have exactly the same propagation constants associated with them. And as we saw was the case with the TE modes and with the parallel plate waveguides in lecture 8, we again will get to values of m and n such that this argument of the square root is negative. The value of that square root is then imaginary, which means that the propagation constant is imaginary, that mode is evanescent, and is cut off. So for some particular frequency, only certain values of, only a finite number of m and n will be able to propagate. And the higher you go in frequency, the more modes that you'll have. Okay, that brings us to an end of this lecture. And this was a long lecture, maybe a little bit tedious as we progress through the steps. And to re-emphasize, I don't expect you to be able to produce that derivation. I expect that most of you should be able to understand the steps as I walk through them. What I do expect you to be able to do is be able to use those equations, which would be provided to you on an examination, and know how to use them to describe the modes that we're going to talk about in lectures 9C and 9D. I also expect you all to be quite completely aware that when you're faced with a new waveguide, one that's a geometry that you haven't analyzed before, that you know the method. The method is, for the TE modes, write the Helmholtz equation for the magnetic field, for the Z component of the magnetic field, apply the boundary conditions, and then use the waveguide field equations to be able to get the other components of the mode. And the same thing for the TM case. In the tutorial, I ask you to step through the process for the TM modes so that you can get a little bit more familiar with this process and get a better feeling for what's going on at the various stages in the procedure.